Daniel.
Welcome. Um, yeah, over to you, Daniel. You can start. You can start your presentation now.
Okay.
We cannot hear you, Daniel. Is are you muted or what? Daniel, we cannot hear you.
Yeah, it's muted. Daniel, unmute yourself.
Wow.
Yeah, okay, now we can hear you.
Okay. Okay.
Yeah, you can start
So
now.
I said this is a preliminary work, but then we've published a version of it,
Okay,
and we are still looking at improving it.
okay.
It's a multidimensional inequality matrix for sustainable business development. It's a joint work with a colleague at the University of Pavia in Italy. So I would be giving I'll be giving an introduction as in a brief background, the methodology, empirical application, and then the conclusion. So now, inequality is a critical global challenge that affects individual opportunities, business growth, and societal well-being. And this is a multifaceted issue that manifests across various dimensions, including economic, social, and environmental aspects. At the individual level, inequality results in uneven distribution of resources, opportunities, and privileges within and across societies. At the corporate level, disparities among firms leads to market concentration, reduced competition, and barriers to entry for smaller businesses, undermining economic growth and sustainability. Now, understanding the diverse dimensions of inequality is essential for crafting effective and targeted policies. But usually, the traditional measures of inequality that is known is the Gini coefficient or the Lorentz curve, the Thiel index. However, these indices primarily focus on single dimensional income or wealth disparities, and it offers a limited perspective to the study of or to analyzing inequality. Now, the single dimension inequality measure often oversimplify the complexity of inequality dynamics in ignoring interaction between different dimensions. And this has led to the advancement in the use of multidimensional approach that reflect the interconnected and broader nature of inequality. And there have been several works in this area. It also led to the emergence of multidimensional approaches like the generalized entropy index, the multidimensional Gini extension, and then statistical techniques like the PCA. There are also policy-driven applications that include the Human Development Index by the United Nations Development Program and the Multi-Dimensional Poverty Index. These indexes integrate dimensions like health, education, and income in the computation of inequalities. Now, the problem with some of these multidimensional approach is that some of them require the use of, as in weights, and some of the weights are very subjective. So it affects so that's why advancement, methodological complexity hinders the practical application of multidimensional measures in real-world scenarios. And this is the area with my colleague we've been trying to work on for the past, as in few months. Now, so this paper contributes to understanding inequality in two key ways. So first, we introduce a novel methodology for measuring. Actually, the measuring has been introduced, but we dealt with it. We take it a bit further. That is not just measuring, but also decomposing multidimensional inequality. The idea is that this innovative method disaggregates the overall inequality into distinct components, providing insight into sources and drivers of inequality. So it is particularly valuable in context where single dimensional metrics fails to capture the complexity of inequality. And the second aspect of the work is to apply our methodology to analyze inequalities in corporate financial performance and ESG adoption among SMEs. So here we focus on some Italian institutions, and this is to provide critical insight for policymakers identifying areas where intervention can reduce disparities and promote sustainable business practices. And through this work, we are also able to link financial performance, corporate financial performance with ESG related inequalities, offering data driven guidance for fostering equitable and resilient economies. Now, so to the methodology, this is the Gini index. And the Gini is the widely recognized measure of inequality that quantifies wealth or income distribution within the population. And it is given by this formulation. In the discrete form is given by the second equation. Now, the problem with the Gini, like we know, is that it is one-dimensional. It is one-dimensional. And what we are trying to look at is trying to look at something which is multi-dimensional that can take us in multi-dimensions whilst as in analyzing capturing the interconnectedness among the various dimensions. Now, so in our approach, we use the concept of the Fourier. So first of all, we have the Fourier one-dimensional inequality index. That's as in is quite similar to the Gini index. And here the Fourier transforms. The use of Fourier transform is important to assess inequality in the frequency domain. So it identifies dominant frequencies in the data distribution. So now, the Fourier one-dimensional inequality index is given by equation 3, where we are looking for the supremum of the Fourier transform, as in minus the derivative or the gradient of the Fourier transform divided by the gradient, as in computed at the point 0. Now, the Fourier transform itself is given by the expression in 4. So what we did here is, now, under the assumption of Gaussian, for a Gaussian probability measure F with mean mu greater than 0 and variance sigma squared, the closed form expression for the one-dimensional Fourier inequality measure is given by another collaborator in one of his work, he's also a professor in Pavia, Toscani. He came up with this idea where the one-dimensional Fourier transform is basically directly proportional to the coefficient of variation. Now, in the paper, we proved how this index was obtained, and we were trying to look at a variant of it, but unfortunately, if the distribution changes, the T, we are not able to get a closed form expression for the student T distribution. So we had to remain with the Gaussian concept. Now, here the T1 would lie within 0 and 1 can be interpreted similar to the traditional inequality indexes, where 1 indicates a higher inequality, 0 indicates a lower inequality. However, in this framework, the limitation here is that the T can be greater than 1. The one-dimensional Fourier transform, Fourier index can be greater than 1 in the sense that because of the top, as in the standard deviation, if the standard deviation is greater than 3 times the as in the denominator, what we are going to have would be greater than 1. And that is the case when we have heavy tail distribution. So this is one of the key limitations, but then it's not necessarily a limitation. It just shows that the Gaussian would not be the best to capture it, but then we are trying to see if there is a more appropriate, or we can find a closed form expression for the student T variant version of equation 5. Now, so this is for the Fourier one-dimensional inequality index. Now, this can be extended to the multi-dimensional case. Extension of the Fourier one-dimensional index to the multi-dimensional case. By extension, this allows for the inequality to, as in, take into consideration the correlated factors. So the Fourier multidimensional index is given by the expression we have here. The psi is a vector. The psi here is a vector, and the 0 is also a vector, as in a vector of zeros. So the gradient of the Fourier transform is given by the expression below. Now, here too, similar to the one-dimensional case, values closer to 1 signify higher inequality, and values as in close to 0 signify lower inequality. Now, the Gaussian version of this, if under the assumption of a multivariate Gaussian distribution with mu as in given by that, and here, even though we can put the fact that mu should be strictly greater than 0, it is not much of a requirement, because the closed form expression we have here is given by is also proportional to the Mahalanobis distance. And since with the Mahalanobis distance, whatever is inside there would always be positive. So this is why the condition on the mu is not strictly binding. Now, unlike the one-dimensional index, the Fourier multidimensional index can accommodate negative values. We mean negative mean values. This is because it relies on the Mahalanobis distance, which measures the distance between a point and a distribution. So the Mahalanobis distance is always positive, regardless of the sign of the mean values. Now, so in another paper, in one of my other papers, I showed that over time, it's been proven that the Mahalanobis distance can also be decomposed into the various as in components of the measure. So using that concept, we now looked at the concept of marginal inequality index. We define the marginal inequality index as a measure of the sensitivity of the multidimensional Fourier inequality index with respect to changes in the mean of the dimensions of the factors. Now, so this can be expressed as the derivative of the multidimensional index with respect to the mean of dimension I. And this is given by the expression we have there. From this expression, there are certain things we can deduce from here. First of all, we see that there is a negative, and the explanation for so the explanation here is the sensitivity to dimension I. The MIF quantifies how changes in the multidimensional index increases changes with an increase in the mean of each dimension. This reflects the impact of dimension I on the overall inequality. Now, the negative sign indicates that an increase in the mean of each dimension reduces the multidimensional index, suggesting that higher means in a given dimension tends to reduce the perceived inequality, assuming other dimensions are held constant. Then we have the covariance effect. The covariance effect, the term, as in the last term, which is the sigma inverse mu, reflect how the covariance structure influences the relationships between dimensions. So dimensions with strong interdependence, that is the large off-diagonal elements in the sigma, may either amplify or dampen the contribution to the overall index. And there is also another benefit in the sense that highlighting the disproportionate as in contributions, the marginal inequality index identifies which dimension disproportionately affect the inequality index. This is particularly useful in systems where targeted intervention in specific dimension can significantly alter the overall inequality. So this is now in terms of application, what with the application, this application study or this study examines disparities in corporate financial performance, aligning with the ESG outcomes, emphasizing multidimensional inequality among Italian SMEs. So here the focus is to look at the relationship between the corporate financial disparities and ESG outcomes in achieving sustainability goals. So traditional unidimensional measures often fall short because they are not able to take into consideration the interactions or the interconnectedness. So this is what necessitated our use of the multidimensional index for a holistic analysis. Now, we obtained annual balance sheet data of top listed SMEs in Italy from 2020 to 2022. And this is sourced from the Mod Finance database. There's a fintech company accredited as a credit rating agency by the European Securities and Market Authority. Now, the data includes ESG scores derived from key indicators of environmental sustainability, social responsibility, and governance practices with criteria that align with the widely recognized ESG standards. In terms of environmental indicators, this include metrics on carbon emissions, resource efficiency, and waste management. For social indicators, it covers employee welfare, diversity, and community impact, whilst governance criteria address board composition, shareholders' rights, and transparency. Now, for quality and reliability of the data, the following exclusion criteria were applied. We excluded records with missing financial data, missing sector classification, and missing ESG scores. We also excluded companies with total assets below 1 million euros and excluded companies with turnover below 1 million euros. So after applying these filters, we were left with over 1,062 or 1,062 SMEs for our analysis. Now, we categorize the SMEs into 5 broader groups following the global industry classification standards. So we have the consumer sector, which consisted of consumer staples and consumer discretionary. We had the financials, which included banks, banking, insurance, and financial services, and real estate. And then we put together healthcare and essential utility services into one group. and then materials and industrial activities also in one, and then tele-inform IT and and communication industries also into one. So in terms of the distribution, the data consisted of 33% institutions belonging to the consumer sector, a few, just about 14 of them, which consisted of 1.32% in banking, insurance, financial services, and real estate. 5.8 with 1.8 within the health and utility, essential utilities. Majority from manufacturing, as in materials and industrial activities, and then almost 6% from the IT and communication industries. Now, in terms of ESG matrix, one of the things, this is a summary statistics, we could see that in terms of the ESG, the financial sector had the strongest, as in the highest ESG score. This is the overall, this is for the environmental score. The first one is the environmental score. The second one is the social score. The third is the governance. The overall is uh, below. And in the overall, we see that the financials had the highest. In terms of the environmental, financials still have the highest. In for social, social seems to be the lowest and the most variable in terms of the values in the parentheses are the standard deviations. So social scores are the lowest among the ESG scores. The governance score is consistent across sectors, but still moderate in terms of reflecting partial standardization. When it comes to the corporate financial performance indices, we took the total asset shareholders funds, which is equity, turnover, net income, and then the earnings before interest, taxes, depreciation, and uh, amortization. So here we see that the health and essential utility sector shows the highest across most financial metrics, with also a greater variability. The tech com sector shows us in struggles with profitability. They were the only sector that recorded as in on average negative net income. Now, going on.
You have 3 minutes left, Daniel.
Okay, wow. Okay, so in terms of the unidimensional ESG inequality analysis, what we observe here is that the financial sector has the highest inequality in terms of the ESG. And this is driven by, we can see that this is driven by social inequality and then governance inequality. The environmental inequality is the lowest. However, manufacturing tends to be the lowest in terms of ESG, in terms of ESG itself. But then when you look at the others, yes, it's quite yes, it's also the second lowest here. Now let's get to the unidimensional in terms of the corporate financial performance. Here too, we see that the health and utilities has the highest inequality. Manufacturing has the highest one-dimensional when it comes to the Fourier index. When it comes to the Fourier one-dimensional inequality, the manufacturing has and we can see that this shows that there is as in variability in terms of the distribution. Now, when we get to the multi-dimensional index, one thing we see is that this is looking at it over the years. We see the consumer sector experiencing rising disparity from 2020 to 2022, whilst the financial sector experienced decreasing inequality from 2020 to 2022. In terms of comparing the multidimensional index with the average Gini, with the average of the Gini index, what we observe is that for a multidimensional index, manufacturing records the highest, whilst financials records the lowest. Whilst for average Gini, financials still records the lowest. Health and utilities records the highest in terms of average Gini. So we could see that here, Gini, we see in terms of the Gini, in some of the single dimensions, it may record the highest, but then when you look at it overall, it may not be the case. When it comes to this ESG, we also recognize that the consumer sector records the highest multidimensional index, whilst the financial sector records the lowest. Whilst in the Gini, financial records the highest, and then the manufacturing records the lowest average Gini. Now, when it comes to the marginal contribution to the overall index, one thing we see from here is that all sectors records negative contribution for environmental, social, and governance, except the financial sector. So the financial sector we see have a mixed contribution to ESG inequality. The social contribution is positive, whilst the environmental and governance are negative. When we look at the corporate financial performance, here we see a mixture throughout, but there's something that we can see from here. That's for positive contributions, we see that between this is mainly recorded by the total asset and then the net income. Net income and total assets as in positively contribute to inequality, whilst shareholders' funds turnover and the earnings before interest, tax, and depreciation contributes negatively to the overall inequality. So in conclusion, here we introduce a methodology that for measuring multidimensional inequality and decomposing the multidimensional inequality to assess the contribution of the individual dimensions to the overall inequality. The result shows sectoral disparities in terms of corporate financial performance and ESG metrics. And then lastly, we see that in terms of ESG score, environmental and governance practices have the most substantial negative impact on inequality, whilst social, scores have a minor positive impact in the financial sector. In terms of the corporate financial indicators, asset and income disparities tend to drive inequality, whilst shareholders' funds turnover and earnings act as stabilizing factors in reducing inequality across sectors. The financial sector shows the most negative earnings before interest, and then the most positive net income contributions to the corporate financial performance. I think I can end here.
Thank you, Daniel.
You're welcome.
Very, very interesting talk. Any questions for Daniel?
Prof, I will want to interact with him small.
Okay.
Thank you, Dan, for a very interesting presentation. I just want to find out some few things on a learning note. You sort of truncated the data, maybe if I should put it that way, by leaving out those that were below 1 million data points and all not.
Yeah.
But then the essence of inequality estimators is to give a holistic appearance or representation of a scenario within a given environment. So just because it happened to be institutions, if it was like, say, in a country or a small area estimation where your concern is of a certain region, you will not necessarily be able to leave out some households, because the policies you want to promulgate should be one that favors the whole or accounts for the welfare of the whole society. So doing so alone also means that it's actually having some impact on the actual evaluation or performance of your models. Then, even with that, you realize that the estimation, the variances of the standard errors of your estimators were very high, which gives an impression that the actual precision of the estimator itself still is much to be desired, even though you had highlighted the difficulties you had with the normal, the Gaussian estimator in developing the model. What do you think we can do to get a balance where everyone is covered? Because I did similar work before, but that one, I even had I was using net income. And it happened that I had negative values and I had to do a lot more, massaging to be able to get through. That's why we are drawing your attention to this.
Okay, thank you very much. You see that, like you rightly mentioned, even in the case where we had to truncate some of as in the turnover and the total asset, you can even see as in the disparities in terms of the standard deviations. So you can imagine if we were including almost everything, then it's going to be as in. But I understand one of the things we were trying to look at is to bring everybody on board, and then to also find a way to maybe look at replacing this guy as in for the unidimensional, instead of looking at as in the standard deviation, because based on the concept of how do we call it, the assumption of Gaussian, if you have very big disparities, as in very big variability in your data, the top guys are going to drive the deviations hugely. So another thing is to find a way to either replace the standard deviation, maybe with some sort of a more robust measure that can capture that. But that is something we are thinking about, whether maybe in terms of maximum, as in the mean absolute deviation or something like that. But with the application aspect, like you said, I'm not sure, because here, if you look at the distribution itself, the reason why we had to truncate it at 1 million is because some of them are within the hundreds of millions, thousands, or as in billions. So taking others that are within lower than 1 million is going to make the result as in, I don't know, but it's going to make it much more difficult than we have now. So this is why we had to truncate it at that point, just to look at the topmost listed, not just everyone. But we, like you said, we can extend it and look at the case where we are looking at everyone.
Okay.
All right, guys. So I think we need. Sorry.
Yeah, I just want to make a proposal and see whether it will make sense in his case. One would be, instead of using the Gaussian, is it possible to use the standard normal? Or probably you log transform the data or use the relative transformation. Maybe it will be able to reduce the standard errors. You may check that in another time.
Okay. Yes, I think that is now the issue is that you see that for some of the let's say in terms of net income, some will be negative. And so it's also that is also another thing. But we can look at other ways to transform it and then see if that would help.
Okay, thank you again, Daniel, for
You're
your
welcome.
inspiring talk. The final talk today will be by a brother originally from Ethiopia, but currently working in Arizona State University in the U.S. Is Hapti. Hapti, are you there? Hapti?
Hello, Professor.
How are you, sir?
I'm fine, and you?
I'm fine, brother, and good to see you.
Yeah, thank you very much.
Yeah. So the title of the final talk today is going to be Robust Principal Component Analysis with Truncated Weighted Nuclear Norm and Adaptive histogram equalization. So Hapti is a faculty at the Arizona State University Biostatistics Department. He is originally from Ethiopia. Over to you, Hapti.
Yeah, shall I continue?
Yes, please.
Okay, yeah. I shared my PowerPoint.
Yes.
Can you see?
Yeah, we can. Yes, we can. Can you put it to the full screen, please? Can you do full screen?
Okay.
Unless he enlarges this full screen in this, it will be difficult for him to get it in this version. I think he's open with the.
How about now?
It's
okay.
Yeah,
so
yeah,
if
it's
you are
better.
done
Yeah,
the
it's
professional
better now.
Oh, wait a minute. Okay.
Okay, just continue. Just continue.
Okay. Yeah. Thank you very much.
Thank you. Hello, are you okay?
Yeah. Wait a minute let me share it. Okay. It's wrong.
Apti, you okay?
Yeah.
What happened? It seems to have disappeared. I don't know what happened. He was here a minute ago.
Who?
This guy, Apti, the guy from.
Okay. Maybe he's having challenge. Maybe he will share again. Let's just give him a few minutes. He will join us again.
Okay. Here he is. He's back. Maybe he has problems with the internet. Hi.
Yeah, possibly.
Are you back, Hapti?
Yeah, he's coming.
Okay, good. We cannot hear you, man. We cannot hear you.
Yeah. I'm trying to share it actually. Can you see now?
Yeah, we can see it now. We can see it, yes.
Okay, that's fine.
Yeah, yeah, we can see it, yes.
Yeah, thank you very much, and sorry for the internet problem. Thank you, Professor Sarles, just for preparing this seminar presentation. My today's talk is about one of the famous approach called robust principal component analysis, assisted with truncated weight nuclear norm and adaptive histogram equalization, particularly in enhancing the quality of medical images. And my name is Haptet Adeselikasa. I'm currently working in the Department of Biostatistics, Arizona State University, under the supervision of Professor Bingen Chen. This presentation has several outlines, the background of the work, the drawback, the contribution, the problem formulation, simulation results, and finally, I'm going to also highlight about the conclusions that we attend, the results we attend based on the proposed method. Coming to the background, medical retinal image processing is widely used for the early detection and diagnosis of human eye diseases, including the diabetic retinopathy, glaucoma, cataract, and the age-related macular degeneration. However, the problem of finding the low-rank components or the true underlying objectives in high-dimensional data is taking an increasing importance, especially in modern applications like in image recovery, in crime detection, background extraction in video processing, in radar imaging, and the bioinformatics. In addition to this, also robust methods are really now getting attention, especially to recover or to find the true underlying object in high-dimensional data. In video processing, especially to extract the background of video sequences, image alignment, especially to put the images well aligned to as well. The enhancement of retinal images, as discussed by Costa in 2070, is also becoming crucial for identifying various medical conditions, mainly to identify the medical condition as in human eyes as a glaucoma, diabetes, or Alzheimer's disease. Also, this is highlighted recently by Cohen. In 2022, Imana just considered a powerful tool called adaptive histogram equalization to improve the detailed characteristics of images by partitioning, which is to mean that there are several approaches developed to enhance the quality of retinal images, but a majority of the methods are lacking, especially in detailing the characteristics of images. So in order to tackle this dilemma, just in 2022, adaptive histogram equalization was employed. However, this method lacks robustness where there are gross noises in high-dimensional medical images as well. Therefore, there is a need to develop a new biostatistical methods for medical research that are also resilient to noise, outliers, heavy sparse noises, and even illumination when imaging the human eye, while also preserving the detailed characteristics of retinal images. This shortly to mean that developing the biostatistical methods is very important, especially to improve the quality of retinal images. That is very useful for early screening and the medical diagnosis as well. As the basic problem, I want to explain this about this one to better understand about our method. Suppose that a person is in crime detection, a person is using a mask and the eyeglass around his mouth and the eyes in order to hide himself from security camera. The question or the major question here is that really possible to prune out the mask and the eyeglass from the human eye, and can really we get the true underlying object by using the modern robust statistics? Mostly the answer to this one is yes. A person used a mask around his mouth in order to hide himself from security camera. By using the deep robust algorithms or modern robust statistics, particularly machine learning and the optimization technique, we can prune out this mask from the mouse and get the true underlying object. This is the major motivational question that is encouraged us to develop or improve the robust PC. So one of the major questions here is how to decompose the corrupted data matrix that is really coming from images. We don't worry about what kind of the image is. It can be natural face images, it may be video sequences, it may be the medical images. That images are just combined into the matrix as M, which is decomposed as low plus L plus E, where L is the low rank component, or L is what we call it in medical imaging, the enhanced images or the recovered images. E is the aggregated errors, which is pruned out from the data matrix. So in this case, by using the modern robust statistics or statistical methods, mainly the machine learning and the optimization techniques, we can recover the corrupted data matrix into the low-rank component and the sparse noise. Here, our objective is to get the true underlying object, the low-rank component. In medical language, we call it as enhanced image, okay? In this regard, thanks to Professor Emmanuel Candice, who is currently working in Stanford University, a professor of statistics and electrical engineering, who developed a robust PCA as a form of optimization problem in 2011. A robust PCA is a breakthrough method developed to decompose the original data matrix into the low-rank component and the sparse error, which is given as such, where the objective is to minimize the rank subjected to the constraint m equal to a plus e. Where M is the original data matrix that is corrupted by adding certain noise or the data is illuminated. And A is the low rank component, the component that we need to find. And E is what we call it is aggregated errors. So in this case, our objective is to minimize the ranks, which means the sum of the nuclear norm plus L with L1 norm, where L is the regularization parameter, and the nuclear norm and the L1 norms are combined together in order to this one. Where A, the nuclear norm is given as such, which means the sum of the singular values of the data matrix, and L1 norm is given as such as the double summation of absolute values of the EIJ. L is the regularization parameter. In this case, A is the low rank component, E is as denotes the sparse noise. This is an optimization problem that we need to get the optimal updated parameter corresponding to the three parameters that we call A, the low rank component, E is the aggregated errors, and this gamma is what we call it is the Lagrange multiplier. There are several approaches to solve this problem. There are several approaches to get the optimal updated parameter corresponding to the three parameters. In this case, the augmented Lagrange multiplier is used in order to solve this problem independently and separately. What is the problem of this work? Even though this problem is just a breakthrough algorithm that decomposes a given data matrix as A plus E, especially in imaging, it lacks robustness when there are misalignment issues. So, inspired by the lack of robustness developed by Candice and Russell, the paper which was developed in 2012, one year later, Candice's work by incorporating a affine transformation, which corrects the misalignment problem. And our recent published article, Robust PCA with Weighted Nuclear Norm, and the paper that we published in 2019 lacks robustness, especially in many aspects. Lack of robustness towards outliers and sparse noises, which means when there are many outliers, when there are many gross noises within the images, the stated methods lacks robustness to improve the quality of images. The other issue is the misalignment problem, which means the Candice work and the previous state of the art of the work lacks robustness, because when there are many misaligned images, especially natural face images, it lacks robustness. So adding a affine transformation is very important to correct the issue of alignment. The existing robust PCA is not showing the detailed characteristics of retinal images, especially medical images. Enhancing the quality of the image is very important, especially for early screening and medical diagnosis. But the problem is detailing the characteristics of medical imaging is very important, especially for medical doctors to learn more about human retinal eyes. So that's why we encourage to combine the adaptive histogram equalization with the truncated weighted nuclear norm. For example, Candice's work is considered the nuclear norm, which is the sum of the singular values, which means that all images have the same singular values, which is not realistic. So, invoked with this motivation, we are developing this algorithm. So the contribution of this work is, in this paper, we investigate the use of adaptive histogram equalization to improve the recovery of retinal images and highlight the detailed characteristics of images, which means to learn more about the blood vessels, to learn more about the detailed characteristics of images is very important. In this paper, we consider the truncated weighted nuclear norm in the robust PCA to reduce the influence of anomalies. When we say anomalies, that means gross noise, outliers, or errors. The truncated weighted nuclear norm combines the benefit of the weighted singular values with selective truncation, making it a powerful alternative to both the standard nuclear norm and the weighted nuclear norm. So this is the contribution. By combining truncated weighted nuclear norm along with the adaptive stochastic equalization combined into the robust PCS framework, this work demonstrated a substantial improvement in noise reduction and clarity in detailing characteristics of imaging. And one of the major questions here is in the optimization problem is the issue of time complexity. In order to reduce the issue of time complexity, we also employed adaptive alternating direction method for multiplier approach is employed to solve the optimization problem, and a new set of updated equations is developed to iteratively update the optimization variables, which was really developed in Stephen again in the very good technique. So the problem formulation here, given an images where W and H denote respectively the weight and height of corrupted images, all of which contains the same objectives. In many scenarios, these images are corrupted by occlusion and the outliers. We can write the individual images in the form of matrix as M equal to this one, which is obtained by taking the vector stacking operator. So invoked by this one, M can be written as A plus E, which means M is the original data matrix, which is obtained from the images, which can be written as A plus E. Actually, this was developed in 2011 by Candice in the form of optimization problem, where A is the clear low rank component. That means we need to get the true underlying object. We need to decompose a given data matrix corrupted by adding certain level of noises as A plus E. So one of the problem with Candy's work and others' work is it does not tackle the misalignment problem. So inspired by this, a file transformation is added into M so that we can get this one. So in addition to this also, the reason why we want to add a file transformation is to correct the issue of the misalignment problem. So in addition to this also, the L1 norm also suffers many problems, especially handling the spatial collinearity between images. So to make the new approach more resilient to outliers and heavy sparse noises, the L2 norm, which combines the advantage of L1 and L2 norm, is also added. So finally, the overall problem can just be posted as such, which means minimize the rank subjected with the constraint, which is equal to this one. In this case, previously the previous work was considered the nuclear norm, the classical nuclear norm, which gives equal weights to all images, and the L1 norm. Now, in this problem, we try to add both the weighted nuclear norm and the L2 norm subjected to the constraint MOT plus the sum of GI change of tau WIT equal to L plus E. The reason why M is modified to this one is by adding the affine transformation, and after a serious mathematical explanation, we modified the constraint. In this case, the weighted nuclear norm can be given as such, which means that the sum of WI sigma IL, where WI is the weights which considers for all images assigning different weights, and sigma IL is the singular value decomposition. In this case, the L2 norm is given as such. By this, the L2 norm has several advantages as compared to the L1 norm, especially in denoising images, corrupted images. What's the problem? Actually, this is a paper that we published recently in 2024 by improving the existing methods. But the problem of this approach is, especially when we come to the medical images, the method struggles to capture the detailed retinal image features and effectively remove noise in high-dimensional images. That means even though this method is decomposing a corrupted retinal images as the low-rank component and the sparse, it lacks robustness, especially in detailing the retinal images, which means in clearly showing the blood vessels in retinal images. So to address this issue, we integrate the truncated weighted nuclear norm with adaptive histogram equalization into the robust PCA framework, which is given in equation 5. Minimize this one, the truncated weighted nuclear norm, plus L1 norm subjected to M adaptive histogram equalization equal to L plus E, where the truncated weighted nuclear norm is given as such, which means previously the robust PCA was developed by someone by considering the classical nuclear norm. Then we tried to improve that by adding the weighted nuclear norm and get the better performance. But the problem is it still lacks when we come to the medical images in detailing the detailed characteristics of the images. So we tried to consider the truncated weighted nuclear norm to further denoise, to prune out the noises, heavy sparse errors in retinal images by adding the truncated weighted nuclear norm and the adaptive histogram equalization. So this is a modified approach.
You have 5 minutes left, 5 minutes.
Okay, thank you. So this problem can also be solved by using ADMM approach similar to the other. One of the advantages of the alternating direction method for multiplier is solving a given optimization problem by dividing into several sub-problems. So by keeping the other parameters as constant, they're solving for one parameter independently. So to solve the optimization problem in equation 5, we employed augmented Lagrangian multiplier function, which is given by this one. After that, we apply the ADMM approach to solve the problems separately. And the L, which means the low-rank component, is updated by using equation 7, whereas the sparse component is updated by equation 9. And the Lagrangian multiplier is similarly updated in equation 11, and the regularization parameter mu is also given by this one. So the idea is the robust PCA was developed in 2011 by applying the classical nuclear norm. So we tried to improve that by adding the weighted nuclear norm combined with the L2R norm and get the better performance. But in medical imaging, detailing the detailed characteristics of the retinal image is very important for early screening and the medical diagnosis to support the medical professionals. So we combined the adaptive histogram equalization with the truncated weighted nuclear norm in the optimization problem form. So in this case, to see the performance of the proposed method, we conducted some simulation by using medical image visualization. And to verify that, we also tried to conduct the numerical simulation to justify or verify how really the proposed method is improved the quality of images. In this case, there are three statistical measures that we employed: the peak signal noise ratio, the relative absolute error, and the structural similarity index matrix, in order to verify the performance of the proposed method, in addition to looking at the visual quality of the retinal imaging. In this case, we used several data sets in order to see the performance of the proposed method. One is the IQ, which is directly taken from the Kigali data set. We also just generate a synthetic data set. We also used the popular databases like digital retinal image vessel extraction and structural analysis for retinal images. When I come to the IQ dataset, it consists of 43,608 retinal images. And this image has two components: the ground truth and the degraded low quality images. Our objective here is to consider the degraded low quality images, and then we apply our method to improve the quality. And finally, we need to compare the improved one with the ground truth. The second data set is we add certain level of noises, which is combined from salt and the pepper together. At 5%, how our performance remove the noises. At 10%, how really the performance of the proposed method is improving the quality as compared to the state of the art of the methods. Up to 25, we tried that one. Again, digital retinal images for vessel extraction is a popular database that I considered for the simulation. Similarly, also STAIR. Here, when I come to the simulation results, this one is the data that we obtained from the IQ database. A is the low rank, the degraded, the original images. It's not the degraded one. So we add 5% of noise to A and got B. And the result attained by our method is C. This one is the method that we attained by our method is C, which means the robust PCA with truncated weighted nuclear norm and adaptive histogram equalization is attained by C. From D to H is the state of the art of the method, which means C is our method, D is the robust PCA with Frobenius norm, whereas E is FGSR, factor group sparse regularization, and F is the LP norm, and the G is the nuclear norm, which means the classical robust PCA, and H is the weighted nuclear norm. That means our previous published article. So visually, when we see the performance of our method is relatively better as compared to all the state of the art of the methods. It better removes the noises added to an original data matrix. Similarly, again, we add 5% of noise here again. This one is B, which means it is A by adding 10% of noise. So C is the result attained by our method, whereas from D to H, it is the results, the recovered or enhanced image from B by the state of the art of the methods. Again, 15% here as well. It is still better performing. And this one is 20%. Now, the difference is very viable here again. C and the H are better as compared to the others. D, E, F, H, R, their performance is becoming deteriorating as the noise level in the retinal image is increasing. And this one is at 25% again. So from this, we can note that the performance of the proposed method is visually better as compared to the state of the art of the method. Here again, this one is the plus the noise level along the x-axis and the peak signal noise ratio along the vertical y-axis. And the noise level is from 5 to 10%. And the peak signal noise ratio looks like this one, which means the yellow represents our method. The peak signal noise ratio is very, very relatively better as compared to the state of the art of the methods. From this, we can note that combining truncated weighted nuclear norm and adaptive histogram equalization in the form of robust PCA optimization problem better the noise, prune out the noises, the synthetic noises added to a given data set. The same thing is happening here as well. The similarity SSIM, still the performance of our method is relatively better as compared to all the others. And when we see the relative absolute error, the relative absolute error of the proposed method is very low as compared to the other. This is to mean that the recovered images by the proposed method is very close to the ground truth, the ground truth, and far from the degraded retinal images. Similarly, we also considered the IQ retinal image recovery. Here in full reference category, A is degraded images, B is ground truth. So we used the degraded image as input and apply our method and achieved C. Whereas from D to H is the state of the art of the method. Visually, our method still seems better. The same thing also by adding another data set here as well. A is the ground truth, the degraded images, which is directly taken from IQ. And the B is the ground truth. And the C is the enhanced image by taking A as input, applying the robust PCA combined with adaptive histogram equalization. The same thing here again. Performance comparison with the state of the art of the methods with the full reference category, figure 10, which means this one, figure 11, this one, figure 12, this one. This one is on the basis of the reference category. So when we see the peak signal noise ratio of our method is far better as compared to the state of the art of the method. And the SSIM is 81, and the relative absolute error is 0.06. The same thing is happening for Fig 11 and the 12 as well. So from this, we can note that the proposed method is better enhancing the quality of a low degraded retinal images, which is to mean that the enhanced images attained by our method is more close to the ground truth as compared to the baseline methods. Yeah. Or in other words, we can say also that the enhanced images far from the degraded images. This one is based on the derived retinal image recovery, which means digital retinal images for vessel extraction, especially for blood vessel extraction. Here we considered A, which means a degraded images, which is directly taken from this database. Then what we did is here we employed our method on A and performed for all state of the art of the method similarly. And B is our method. From C to G is the baseline methods. For example, if we see the second row, the second column, the blood vessels attained by our method is better as compared to all the baseline methods. So here we can observe that the power of the adaptive histogram equalization, which means in clearly detailing the characteristics of retinal images. The same thing is happening here for based on STER database. A is the degraded image, B is the enhanced image by our method, C to G is by the baseline methods. For example, if we see the last row, the blood vessel attained by our method is relatively better. It is more detailing the detailed characteristics of A. So what is the conclusion here? In this study, we considered a new method that incorporates truncated weighted nuclear norm along with adaptive histogram equalization for retinal image enhancement. And the ADMM approach is employed in order to solve the optimization problem, in order to get the optimal updated parameters that we call L, E, and the Lagrange multiplier. This is very important, especially to reduce the issue of time complexity, as it is solving the problems in a round-robin manner, iteratively. And conducted simulations shows that the proposed method outperforms to the state of the art of the methods based on the public available data sets, including the synthetic generated data set. Thank you very much.
Thank you, Hapti. Thank you.
Thank you.
Any questions for Hapti? Any questions, sir? Yeah. Okay, if there are no questions, that's the end of the session for today. Tomorrow we have another full day of talks. Thank you for everybody who presented today, including Emmanuel, Ricardo, Owen, Alex, Victor, Jackprick, Kingsley, Tolu, Daniel, and finally Hapti. All of those presented very interesting talks today. 2 people missed out today. Hopefully we can include them in the program for tomorrow. Okay, hopefully. And so tomorrow we have a full list of talks starting from 10 a.m. UK time. So the first talk will be presented by Adam, and it will be followed by other people. So hopefully we will have a very interesting day tomorrow. So I'll see you all tomorrow. So have a very good night.
Hi, Prof.
Okay.
Before you end this section, Prof.
Yes.
I don't know, maybe if we are to discuss tomorrow, Dr. Edson drops a message before leaving in the morning regarding a grant. I don't know whether you see that.
No, I didn't see it. What was it about?
He said it's about grant. There is a grant that he share a link with us. That is important to see how to collaborate because he's busy. He cannot wait to the end of the workshops.
Do you know when the deadline for the grant is?
I have not checked that. Maybe we'll discuss tomorrow before, maybe
Yeah,
after the
maybe
presentation.
we can discuss that with Kingsley and other people tomorrow. If we finish early tomorrow, we can discuss that. So depending on how many people turn up, and also depend if Samuel Manda and Dr. Moose turn up tomorrow, then we need to add them to the program because those are two people who did not turn up today for the talks. So
Yeah.
hopefully they will turn up tomorrow. But yeah, the grants are something, as I said at the beginning, the introduction to the workshop. I mean, grants and papers and everything. We need to redouble our effort. For HAPTI too. HAPTI, I know you're at Arizona State. There are many opportunities for writing grants, brother. We need to help our brothers and sisters in the continent by writing grants. So that they can do meaningful research, they can do impactful research that make changes to their communities and to the countries. So let's look for opportunities for writing grants in addition to writing papers. So that's something we should discuss in the days following the workshop. I mean, I think in the last year, that is 2024, we did a lot of work. We wrote a lot of papers and we were also successful in getting some grants, but we need to do that 2 times, 3 times, or even 10 times in the 2025. Okay.
Okay. Thank you. Yeah, I will take part in tomorrow's seminar conference presentation as well, and I'm also very happy to be involved in Garan research writing as well. Thank you very much, Professor.
Thank you, Hapti. Have a good time, man.
Okay,
all right, guys. All of you have a good night and a good evening. I will see you guys tomorrow, 10 o'clock UK time. Okay, 10 okay. Thank you,
Thank you so much.
Thank you, Kingsley. Take care.
Yeah, thanks, Prof.
Thank you.
Yeah. Good night.
Good night.
Yeah, is Edith the one Edison introduced to you?
Edison.
Yeah. The last person he just introduced to you, Ume from Nigeria, Nnadi University as well.
Okay.
Yeah.
Yeah, I know. Yeah, he studies with me. Yes, Adam. You mean Adam? Yeah, he studies with me. Yes, yes, madam.
Yeah.
Yes.
I just want to thank you so much. I joined in the program today. The workshop is very interesting.
Thank you. Thank you.
Thank you so much. Thank you so much.
Thank you.
Yeah. Good night.
Good night.
Yeah, good night. Thank you.
Thank you.
Yeah, thank you.
Bye.
Thanks.